Hello, my name is Jason. I'm a security researcher and general troublemaker, and I'm going to talk to you today about something I made called Smuggle Bus. Smuggle Bus is a tool for bypassing file type restrictions and thwarting file content inspection in a simple and elegant fashion. It's intended for use in pen tests as well as to demonstrate weaknesses in current security solutions in hopes that this may spur improvements. The underlying principle of Smuggle Bus is hiding files by merging their contents with that of other files. It is essentially a very exceedingly simple form of steganography. Smuggle Bus takes the contents of two files and puts them together into one file. This is so basic, it almost seems silly to talk about it, but it is amazingly effective against even very expensive security tools, and I think the fact that it is so effective is fascinating and important for us to consider as security professionals. To illustrate this, we'll look at a basic example, a JPEG and an unencoded, obviously malicious binary created with MSF Venom. If we upload this malicious binary to VirusTotal, you see that it's easily recognized by pretty much all AV vendors. However, if we simply append the contents of the malicious binary to the end of the JPEG, then upload the combined file, you'll see that comparatively few AV vendors still recognize it as malicious. The file is typed as JPEG, it'll render as a JPEG in image viewers and browsers, and for all intents and purposes will act, and indeed is, a normal JPEG. The malicious binary on the end has no effect on the functionality of the preceding benign file. If we want to get the malicious binary back out, we can do so easily as long as we know its length in bytes. We just take the last x bytes of the combined file, where x is the length of the malicious binary, and put that wherever we like. As a bonus, what do you suppose happens if, rather than appending the malicious binary to an entire JPEG, we do something even more simple, like add a single space at the beginning of the malicious binary? Do you think that should make a major difference in AV detection? Well, let's see. Incredibly, the simple act of adding a space to the beginning of a malicious file nevertheless causes many AV engines to no longer recognize that file as malicious. The original binary had 45 detections, and adding the space cut that down to 14. And notice that many of the big name vendors aren't showing detections. We'll explore why this may be in just a bit. But I want people to realize this and to consider what this says about how these tools actually work and how they, and no doubt other tools, are developed. Now that we understand the trick at the heart of it, let's talk through Smuggle Bus itself. In basic mode, Smuggle Bus takes one or more files you want to hide, called contraband files, and sandwiches each of them between a full-length benign mask file, either one you specify or a randomly generated image, and the last 16,000 bytes of that same mask file, along with a label that lets you find it afterwards or get the contraband file back out. This ensures that both the beginning and the end of the file will look like the mask file. Likewise, you can use Smuggle Bus to search for any files you know the label for in any directory you have access to, and extract them. Smuggle Bus supports searching for multiple labels at the same time, so you can create a whole bunch of them, scatter them to the winds, and then search for any and all of them on any hosts you have access to. Smuggle Bus also supports an encrypted archive mode, which takes your contraband files and places them in a double-zipped, randomly named encrypted archive before sandwiching them in the mask file, along with the label and the archive password, either one you supply or a randomly generated one, and afterwards allows you to easily find and extract the encrypted files. Finally, there's also an alternate version of Smuggle Bus that's designed to smuggle and execute PowerShell scripts. This version takes a PS1 file as its input and conceals the script inside an archive that is then sandwiched inside a mask file. Afterwards, you can extract the script from the mask file and execute it from memory via the PowerShell commandlet invoking expression. In order to minimize detectability, Smuggle Bus uses a variety of techniques to break up strings and randomize/obscure the unencrypted bits of data hidden in the file. This makes it much more difficult to find such files via signature or strings analysis. Some examples of where Smuggle Bus may be useful/enlightening are as follows. Many companies rely on proxies to block downloads of executable or other file types. Likewise, email filters will often block executable, encrypted archive, and various other file types. This can be an obstacle for those who need access to a file likely to be blocked and don't have the ability to bypass the security control entirely. Smuggle Bus can evade these by hiding executable or other restricted content in a file type permitted by the filter, typically a JPEG, but it could be anything. Downloading or emailing the combined permitted file/forbidden file, and then extracting the forbidden file from it afterwards. If hidden in a JPEG or other image file, such files can be retrieved simply by viewing a website that incorporates such an image as a site element, and allowing a regular browser to cache them. Alternatively, the file can simply be downloaded or emailed while they're hidden in an otherwise permitted file type. This will also bypass email attachment sandboxes and other such security and analysis solutions, as the combined file will not exhibit any malicious behavior when detonated, and, when used in archive mode, will not contain any strings or byte sequences that might flag a Yara rule or other such solution. Smuggle Bus can use any file as a mask file, but hiding payloads in images, MP3s, and other media files allows you to distribute them to a wide range of unsuspecting users via browser caching or downloads from any number of websites. This allows you to, at some point afterwards, find and extract the payload you need that is already on the host that you're targeting. This does still require some kind of execution on the target host, such as a Smuggle Bus off-mode dropper, but it avoids having to call out to a C2 server in order to transfer your payload to the target. This allows you to avoid many of the things that trigger suspicion in existing detections, because neither the dropper nor the payload manifest any malicious behavior in isolation. Analysis of the dropper will show it search a few directories and then exit without effect. Analysis of the mask file containing the payload will show only the benign functionality of the mask file, while the malicious payload inside will be encrypted, assuming you use the archive function. It is only when both are analyzed together that any malicious activity will manifest. For example, consider a malicious site that includes a function inviting users to enter their email address in order to receive something. In such a case, you would know that anyone who enters will have visited your site and thus cached your images and malicious payloads, and that they have specifically requested something from you, thereby giving you the ability to put your dropper in the message you send them and know that they will be much more inclined to trust it. You would also have their user agent string and source IP, and thus a reasonable amount of recon info on them, allowing you to target their specific browser/operating system with specific secondary payloads hidden in multiple images they cached when they first visited your site, or simply avoid targets you're not interested in, thereby preserving the reputation for your site. One important note for this, however: if you choose to deliver contraband via browser caching, make sure that the image file you use is larger than 16 kilobytes. Files smaller than that will generally get cached in block files rather than as individual browser files, and won't be easily extractable. Many companies rely on data loss prevention and other such controls to monitor uploads for protected data, such as PII, PHI, and so forth. Smuggle Bus can evade these by hiding the exfil content in a benign file that can then be uploaded, emailed, or otherwise sent outbound. The wide variety of sites that allow image and other file uploads offer a nearly infinite variety of exfil vectors. The concept of archiving sensitive data in an encrypted archive and exfiltrating it from a network is quite familiar, but it's also quite obvious. A large zip file headed outbound is a rather glaring giveaway that something is up. The benefit of Smuggle Bus exfil is that it allows exactly that, uploads of encrypted archives, but disguises them as a less suspicious file type. This rather simple change can nevertheless bypass alerts that rely on file type, as well as fool even vigilant security analysts by blending in with normal and benign traffic. Uploading a fully functional JPEG that doesn't depict anything sensitive or restricted from a user's computer to a site hosting JPEGs will present a very plausible picture that only the most paranoid analysts will dig into. And even then, the nature of what was done will prove elusive without detailed forensics, because the only non-encrypted indicator of malicious activity will be, at most, unusual raw amounts of data leaving the network. First, we'll demonstrate Smuggle Bus in its most basic form, simply taking the contraband file, in this case meterpreter2.exe, and sandwiching it within a random JPEG. Even with just this, we bypass the vast majority of AV engines in VirusTotal. Next, we'll demonstrate Smuggle Bus's archive function, taking and encrypting the contraband file into a password-protected archive, and then sandwiching it within a random JPEG. No AV engines detect even a trace of the contraband file. The file appears as a benign, fully functional JPEG with no malicious indicators at all. It can be viewed and cached via browser, uploaded to any site that allows JPEG uploads, and generally moved freely back and forth across even a guarded perimeter. Note that this function requires that the host have either 7-zip or WinRAR installed. Now that we have our combined file, we need to get the contraband file back out. This is done by flipping the mode of Smuggle Bus to off and supplying the label we got when the file was smuggled in the first place. Smuggle Bus supports multiple labels, so you can feed a whole list of them and it'll look for each and extract any it finds. For our demonstration here, we're going to highlight the cache smuggling route. We'll put our combined file on a web server we control, then browse to that site. Note the image we see. Now we'll run Smuggle Bus in off mode, specifying the label we got, and the Chrome cache is our bus path. As we see, the extracted file is the same. Once again, the trick behind this tool is very simple. What happens if we append a malicious file to the end of a benign file, like an image? Will the image still open like an image? And will computers and security systems recognize that combined file as an image? And as we saw, it turns out that they do. Appending a malicious file to a benign image file will result in a fully functional image that will indeed fool even very expensive security systems. So we might next ask ourselves, why is this, and what can we learn from it? Computer files are just sequences of bytes on some storage media, plus a file system entry that stores information about the file and where the file's bytes are stored on the storage media, usually in a range of locations, which is why hard drives can become fragmented over time. So the only difference between two files and one file is whether the byte sequences are stored in two file system entries or one. If a sequence of bytes is stored under one entry, it will be read as one byte sequence by everything downstream of it. Additionally, when an operating system or application or anything else interacts with a file, it will determine the file type by reading the first few bytes of the file's byte sequence, the so-called magic bytes. Different file types are labeled by different magic byte sequences. You can corrupt a file and make it impossible for the OS or applications to read simply by changing or removing these magic bytes. And you can change the file type the file is read as by changing these magic bytes. If you change the magic bytes of an executable to those of a JPEG, that file will be read as a JPEG. Doing this would quickly result in an error, of course. An image viewer may try to read an exe with the magic bytes of a JPEG, but when it tries to render the contents of the file, they'll quickly break the parameters of the image viewer and result in an error. But the image viewer will try to render it. In fact, a great deal of effort has gone into getting the image viewer to render the image, even if it's corrupt or incomplete or otherwise mangled. You can play with this by opening an image in Notepad++ and deleting a bunch of it, starting from the end and working backwards. It's not until you delete almost all of it that image viewers will start being unable to display at least something. And this is true in pretty much all file formats. The reason this happens is because the goal of these pieces of software is functionality, not security. The goal the people who developed the software had was getting something done, even if something wasn't 100% right, rather than making sure everything is correct and only proceeding if everything is verified. This makes sense when you think about it. If you're trying to sell image software, you want it to render as many kinds of images as possible, and you want it to work as much as possible without the need to troubleshoot. Even taking a step back, I think a lot of us today fail to appreciate the degree to which errors and glitches occur in large amounts of data. Anyone who has tried to transfer a large image file across a network for forensic purposes probably has stories about how annoying it is, because an image is only forensically viable if the hash matches before and after transfer. But because even a single changed bit will change the hash, it's often quite difficult to complete such a transfer. Because for such large files, the odds of at least some small change are quite high. So tolerance of error and bias towards some result rather than no result are integral components of computing, and almost everything has been built on this principle. In fact, a lot of things in the world would probably stop working if we only allowed things that were 100% correct to proceed. But this means that if someone today is trying to be more integrity conscious, unless they literally design everything they're using from the ground up based on this principle, they are eventually going to fall back on some element that has a bias towards error tolerance rather than data integrity. And from that point on, they are slaves to the assumptions of the components they're using. Hence, why so many AV engines are thrown off by something as simple as an added space at the beginning of a file. Many of them are most likely relying on some function that relies on magic bytes with a high tolerance for error, and hence, they inherit that error tolerance and lose the ability to see beyond it. This tendency is compounded by the way profit-seeking businesses operate. On the vendor side, businesses are only required to make products that are good enough to make the sale. Once a product can be successfully sold, any extra effort towards improving it is not just unnecessary, but undesirable, because it cuts into the profit. Willingly adding improvements that cost money for free is unthinkable for a profit-seeking organization. It is only when a product cannot be sold as is that a business will be forced to expend effort restoring it to a state of sellability. If we take an idealistic view,
This should occur via competition, and it should result in innovation. A competitor enters the market and makes a product that is better or cheaper, which cuts into sales of the established business, which forces it to improve its product and/or offer it for less in order to compete for market share. More realistically, however, it is far easier and cheaper to simply mislead customers, and this is what most businesses do. Rather than dig into the underlying cause of issues and root them out, businesses can simply change the appearance of their product and vaguely hint at improvements under the hood, even if there really aren't any. Carefully manicured sales demos that heavily imply the product can do something it can only do in the specific test cases of QA checks and sales demo are infinitely cheaper than reinventing entire sections of a product. On the customer side, everybody is looking for a way to get rid of their problems. Companies want to let someone else do as much of the work they're getting paid for as possible. Teams want to let someone else take responsibility for as many features as possible. Individual employees tend to be the most resistant to this because many of them actually do care about things other than pure profit. But even they have every incentive to avoid dealing with any problems they're not explicitly forced to confront, whether forced by a boss or their own conscience or sense of professionalism. This means that everybody on the customer side is as eager to believe a vendor's pretty promise as the vendor is to make pretty promises, and rely on extremely specific legalese in the actual contracts to make sure they aren't actually held responsible for anything they may have implied in the course of the sale. Both sides are eager to buy into a shared fantasy. Buying this product is less work than thinking.
As security professionals, we need to think about all this as we proceed. Red teamers should spend time thinking about which lower-level functions security appliances are relying on and how they can fool these lower-level functions and thereby bypass the security requirements. What would the developers of the security appliance be eager to believe in order to make their job easier? How would they decrease the range of what they're responsible for? And where is the gap between their assumptions and the assumptions of the people who designed the lower-level function? Blue teamers and security-conscious developers should think about whether the tools they're building are inheriting biases, blind spots, and vulnerabilities from the lower-level components they're relying on, and how the very structure of their teams and dev cycles are biasing them towards these sorts of weaknesses. Don't just think who is responsible for what. Consider who is not responsible for what, and what things end up without any owner in the game of not it that teams play. Anyway, I hope all this has been interesting. If so, please check out Smuggle Bus and let me know what you think in the comments. Thank you.